Hi everybody, this is video I5. It's now the start of section 4.6 entitled Optimization. And the idea of optimization goes like this. Let's say you have something like the volume of maybe a cylinder or something that varies depending on the radius or the height or whatever x may be. And maybe it's not a cylinder, maybe it's some oddly shaped object. And if you were to plot the volume relative to that dimension, you might get a weird curve. So as the volume, or as this x increases here, the volume goes up, but for whatever reason, maybe as x gets bigger here, it goes down. But anyway, in order to find the biggest value of the volume on a given part of the domain, okay, what you're looking for is a maximum, like right there or right there. Or maybe you want to find the lowest value of the volume on a given part of the domain. Maybe the domain's limited, and so that would be a point like that. In any case, typically the maximum or minimum will occur either at an endpoint of the domain or at a max or min. And so with the real life problems that we'll be doing, it's most typical for the optimized point to be at a max or a min, in which case we're going to look for points on these problems where our first derivative is equal to 0. Okay, so let's go ahead and do problem 1. This is the only problem we'll do today. We'll do one a day, quite long problems. So squares are cut from a 12-inch by 12-inch piece of tin. So a square piece of tin. And that says tin. I don't know what I'm doing right now. There we go. The remaining tin is then folded into an open-topped box. How large should the squares be in order to maximize the volume? Okay, so the first thing we have to do is maybe draw a picture of what's going on so we have a sense of this. So I'll do that right up here. I have a square of tin. It's 12 inches on a side. I'm going to cut little squares out of the corner. And I don't know how big they are, so I'll call each x, and since they're squares, each dimension would be x. Okay, that would make this length right here the whole 12 minus 2 of these x's. So that length is 12 minus 2x, this length is 12 minus 2x, and so forth. What we're going to do is then fold these little flaps, because these squares are now gone. We're going to fold these flaps up, and we'll get something that looks like this, an open-topped box, the height of which will be x, and each dimension of the base is 12 minus 2x. So what we want to do is find a formula for whatever it is we're trying to maximize relative to what we're looking for. Okay, and so the volume of a prism is just the base area times the height. Okay, and so the volume of our open top box, and it's a function of x, will be the height, I'll do that one first, times the area of that square base, which is 12 minus 2x squared, but I'll write it like this. Okay, and so this is what we want to maximize. We want to find the biggest possible volume. So I'll let you guys do a little bit of work with the algebra here. If we distribute it all, simplify it, I get the volume is 4x cubed minus 48x squared plus 144x. Okay, so I want you to think about that. It's a cubic and it's positive. We know what this graph looks like. Not only that, we know two x-intercepts right off the bat. Okay, think about this. Okay. Wouldn't the volume be 0 if the height of the box is 0? So if I'm graphing, now maybe I don't know a bunch, but if I'm graphing this cubic, I know one point is 0, 0. But the volume would also be 0 if this side length is 0, and the side length would be 0 when x is 6. So I know I have another x-intercept at x equals 6. So, and not only that, think about this. X equals 6 is a 0 with a multiplicity of 2, so I get a bump off the graph right there. I kind of know what my graph looks like. So what I'm looking for is the peak right there, the highest possible volume. What's the x value right there? Now this isn't a perfect picture, but to find the x value right there, all I have to do is, well, the slope would be 0, so find the derivative and set it equal to 0. So v prime of x is 12x squared minus 96x plus 144. I want to set it equal to 0. I can divide by 12. I can factor this. And we knew that would be a factor because look, isn't the slope 0 at that minimum? Okay, so the only other place where this would be 0 would be at x equals 2. Now think about the domain of this function. We don't have to test the endpoints. The domain, and maybe I should do it in IB notation, does not include 0 and 6. It can't be greater than 6, it can't be less than 0. And so there we have the length of each square. And let's make sure we read the question correctly. How large should the squares be in order to maximize the volume? So we are finished. You would say if you were to answer with a full sentence, maybe you would say, using units, the squares would each be 2 inches on a side. So what I would like for you to do now is I would like for you to attempt, let me see if I can cover what I want to cover, attempt the problem that we're going to start tomorrow. And I'll give you a couple of formulas with it, but there it is. This is the problem I'll be working out tomorrow. So check back in.